Hello kids, today is April 11th and we're going to continue on in our algebra journey. We're in section 10.8, which is entitled Multiplying Radical Expressions. Before we begin, does anyone know why the chicken crossed the basketball court? Well, he heard the referee calling fouls, so he came. And we are in section 10.8, Multiplying Radical Expressions, page 428 of Algebra 1 from Bob Jones University Press. We're using the second edition. And what we've done in the past is we've been multiplying exponential or multiplying variables that can include exponents in them. And we're going to do this where we are multiplying together. Some of the factors that we multiply are radical expressions. Here this is just simple distribution. 4x squared times yz squared becomes 4x squared yz squared plus 4x squared times 2x squared y. 4 times 2 is 8. X squared times x squared becomes x to the fourth, and y. And it's these principles that you've already learned that we're going to be expanding on in this section. So let's go ahead and remember that a radical expression is simply an expression that includes a root. We have the square root of 4x squared, though the simplified form of this is 2x. This is a radical expression here because it includes this radical symbol. We're asking to find the square root of this product here, 4x squared. If we look for the cube root of something like this, that's also a radical expression. This is also a radical expression. Radical expressions are the notation, the writing that we use when we're finding a root of a particular expression. And these work just the same as our rational expressions do, as our algebraic expressions do when we're multiplying them. So let's go ahead and do this first example here. It says multiply the square root of 5 times the square root of 3 minus 2. And this is example 1 in section 10.8. This is simply the distributive property. We have a factor on the outside that we multiply against each individual term in here. So when you have the square root of 5 times the square root of 3, we learned a very important principle. It's called the product rule for radicals. Product rule. Product, of course, is what you have when you multiply two expressions together. And this says that if you have the square root of x times the square root of y becomes the square root of xy. What we have right here is the product. We're multiplying together two roots. Right here, with the square root of xy, we've multiplied those two factors together before we take the square root. There will be some times it will be more advantageous to take the square root of the product. There will be other times it will be more to your advantage to take the square root of individual factors. But these two ways of breaking the factors apart, of breaking this radical expression apart, are very valuable, and that's what we're going to use here. We have the square root of 5 times the square root of 3, so that's going to become the square root of 15. The square root of 15. Now we have square root of 5 times the negative 2, that becomes minus 2 times the square root of 5. It's the square root of 5 times the negative 2. So just like you wouldn't write a2, you write that as 2a, where the coefficient is in front of the variable. When you're working with radical expressions, the rational part, the 2, is in front of the irrational part of the radical symbol. Now, you remember that if we're going to add or subtract, whatever these things are called, if you're going to add or subtract radical expressions, the radicals have to be like radicals. Well, how do you determine if a radical is a like radical? Same way that you determine like terms. 2x plus 3x squared plus 4x plus y. When you're determining like algebraic expressions, the variable has to be the same. Not only does the variable have to be the same, but the exponent right here also has to be the same. So even though we have 3 terms that have x's here, this center term is not a like term because it's a 3x squared. The y is not a like term because it's a y, not an x. So we would add the coefficients here. 2 plus 4 is 6x. We would put our x squared term first. 3x squared plus 6x plus y is how we would simplify this algebraic expression here by identifying like algebraic terms. Well, same thing here. Except here, the number that's underneath the radical sign, do you remember what that's called? Well, that is called, and I didn't write that very well, that's the radicand, R-A-D-I-C-A-N-D. The radicand has to be the same, and the index has to be the same. Now, where's the index? The index is the number that's right there. This right here is read the cube root of 8, so the index is a 3. What's the index if there's nothing written here? Well, if there's nothing written there, it's a 2 because it's talking about the square root. So both the index and the radicand have to be the same for these radical terms to be like radical terms. Are they? Well, obviously 15 and 5 are not the same. So even though these are both square roots, they're not like radicals, so you cannot do anything further with them. The answer to example 1, therefore, is square root of 15 minus 2 times the square root of 5. So let's move on and look at example number 2. Square root of 7 plus 2, square root of 3 minus 6. Let me go ahead and erase this because it's a little bit longer problem. This is example number 2. And it is the square root of 7. Now you explained to me why I just wrote a 3. It is the square root of 7 plus 2 times the square root of 3 minus 6. Now if you look at that at first glance, it might look a little bit ugly with these radical symbols in there. But what do you notice about this? Well, you notice that there are 2 terms in each factor. So these are binomial factors. Remember, binomials have 2 terms in them. When you have the product of 2 binomial factors, you learned that you were able to use this really neat acronym here to come up with what the product was. You used FOIL. You multiplied the first terms together, the outside terms, the inside terms, and the last terms. You took all 4 of those products, which are called partial products, you added them together. So, what do we have when we multiply our first together? You have the square root of 7 times the square root of 3. When you multiply our last terms together, you have square root of 7 times a minus 6. So you have minus square root of 7 times 6. And when you do your inside terms, you have plus 2 times the square root of 3. And our last term is plus 2 times the negative 6. So it's plus 2 times the negative 6. Make sure, yes, that's all on there. Now, you don't have to write out all of these products in this form, but I just want to have it written on this one so that you're very clear what I'm doing. Square root of 7 times the square root of 3 using our product rule becomes the square root of 21 minus, we have 6 times the square root of 7. We want to put that in proper order. Since these are two factors, it doesn't matter if you have the square root of 7 first or the 6 first. But since we want to put our rational factor first, we're going to change that to minus 6 times the square root of 7. Plus 2 times the square root of 3, there's nothing you can do. Plus 2 times the negative 6 is minus 12. Now, is there anything that we can do to simplify or reduce? Do we have any like factors? Like terms? Well, square root of 7. 7's a prime number. There's nothing you can do with that. Square root of 3 is also prime. Nothing you can do with that. Cannot combine these two center terms because these are not like radicals. Well, let's look at this. Square root of 21. Remember, when we're talking about square roots, we're looking for a factor that is repeated. Well, 21's not a prime number, so how do you factor it? Well, it's 7 times 3, neither of which are prime. So there are no like factors here. I'm sorry, there are no like terms here. Nothing in common that you can factor out. So, believe it or not, there is nothing that we can do to simplify this. Now, I want to point out that I said this was example number 2. This really wasn't example number 2. This is just an example that I worked for you because this should have been times the square root of plus the square root of 2. This is still a very valid example for you to see. Let's go ahead and see what would have happened if we did this one. Where we had an extra radical, I really want to write 3 instead of 7 for some reason. Square root of 7 plus the square root of 2 times the square root of 3 minus 6. And let's make sure that I've copied that exactly correctly in case you want to go back to your book and verify that what I'm doing is correct. Well, first we're multiplying square root of 7 times the square root of 3. We already know that's the square root of 21. The outside terms, square root of 7 times the negative 6 minus 6 times the square root of 7. The inside terms, the square root of 2 times the square root of 3. 2 times 3 is 6. Minus square root of 2 times the negative 6 becomes minus 6 times the square root of 2. And if you look in your book for example number 2, you'll see that this is exactly what they have. And the point that I really want to illustrate in both of these problems is that sometimes, particularly when you're working with radical expressions, you can come up with a product that just looks like a mess. Really messy. Surely you ought to be able to do something to make it look more simplified or more cohesive or more tied together. But this is just all there is to it. So you have to be very comfortable with your algebra so that when you get something that looks like surely that answer has to be wrong, and you go back and you look at it again and you figure out that no, it's not wrong, it's just a strange looking answer. So let's continue on. We're going to multiply this. Square root of 5 minus square root of 7 times the square root of 5 plus the square root of 7. Way back in chapter 8, I believe section 7 we started with them, we were talking a lot about special products and identifying perfect square trinomials, the difference of two squares in particular, and what you learned about the difference of two squares. And this is something that is a shortcut. What we have here, we're multiplying two binomials together. You can go ahead and use FOIL to solve this. You have the square root of 5 times the square root of 5 plus square root of 5 times square root of 7 minus square root of 5 times square root of 7. Let me put a couple of little parentheses in here. Minus square root of 7 times the square root of 7. Okay? This becomes the square root of 25 plus the square root of 35 minus the square root of 35 minus the square root of 49. Okay? Should all be all right at this point. Square root of 25 is 5, plus 35 minus 35, they cancel each other out. Square root of 49 is 7. 5 minus 7 is a negative 2. And that's how this would work out if you would take the time to solve this product of two binomials by using FOIL. However, if you realize, this is a special product, this is the factored form of the difference of two squares. You recognize that the first term and the second term of both binomials are the same. They differ only by the sign in the middle. That's the difference of two squares. So what this factors into is the first term squared minus the second term squared. Or 5 minus 2, sorry, that was minus 2 is the answer. 5 minus 7, or negative 2. You arrive at the same solution much more rapidly. You wouldn't even have to write this down because, difference of two squares, square root of 5 squared minus 7 squared, negative 2. So it's to your advantage, like I said when we were doing chapter 8 and chapter 9, it's to your advantage to be able to recognize special products. It shortens the time that you spend on your work, and it helps train your brain to recognize these special products. Let's go ahead and do this one right now. Example number 4, the square root of 3 minus 2 quantity squared. What you have here is a perfect square trinomial. Perfect square trinomial. If you recognize where you have a factor, a binomial factor that is used twice, the solution to this is the first term squared twice the product of the first and last terms plus the last term squared. This middle sign here is the sign that's in your binomial factor. If you have the form A and B. So what this really says is when you have a binomial factor that is repeated, first you square the first term. And then you take the product of those two terms, minus 2 times the square root of 3, and you double it. Minus 4 times the square root of 3. And then you square the second term, plus 4. Okay. The square root of 3 squared, when your exponent and your index here, which is a 2, even though we don't write it, when those agree, your solution is always the radicand, the number that's underneath the radical sign. 3 minus 4 times the square root of 3 plus 4. Now that's just not looking right to me. 3 minus 4 times the square root of 3 plus 4. Let's go ahead and combine our whole numbers. 7 minus 4 times the square root of 3. Once again, you can still go ahead and go through the extra work of using FOIL to come up with this product. If you recognize that it's a perfect square trinomial, you square the first term, you square the last term. You multiply these together, minus 2 times the square root of 3, and you double it. And you get the answer. So let's see what we want to do next on page 430. Page 430 says, multiplying radical expressions. Follow the same rule that you use for multiplying polynomials. After you multiply, simplify the radicals and combine like terms, which is what we've done here. There's nothing new that you're learning in this section. You're just applying it to factors that include radicals. So what do you do when you have 3 binomials that you're multiplying together instead of 2 binomials? Well, same thing that you would do if you had 3 algebraic binomials. You first multiply 2 of them together, and then you multiply that product with the second one. This is example 5 on page 430. This says multiply square root of 3 minus the square root of 2 times the square root of 3 plus the square root of 2 times the square root of 6 minus 4. This time I want to make sure that since there are 3 factors involved here, that I've gotten everything written correctly. Square root of 3 minus the square root of 2. The square root of 3 plus, and I had to squeeze that little thing in because I was going to forget the radical sign, plus the square root of 2. Square root of 6 minus 4. Okay? Multiplication is associative. Doesn't matter which ones you multiply first, how you group things together. Though, by following order of operations, when we have just multiplication, we'll proceed in order from left to right, generally. What I notice here, and I think that this is so messy, I want to clean that up. Square root of 3 plus square root of 2. What I noticed right away, I have 2 factors that differ only in their sign. This tells me this is a product of 2 squares. I'm going to use the shortcut way to multiply these, so I'm going to take advantage of the fact that when you have the factored form of the difference of 2 squares, which is what we have, it's just the first term squared minus the second term squared. Now this is a case where I would change our standard order of operations where it says multiplication in order from left to right. If I had the square root of 3 minus the square root of 2, and for our final product here, square root of 3 plus the square root of 2, I would say, oops, those 2 multiply easily together. You know, just like when you're adding, you learned how to group tens together. When you're multiplying, you learned how to multiply so that the products were convenient. We have the difference of 2 squares here. Difference of 2 squares. It's the square of the first, 3, minus the square of the second, minus 2, times this final factor here, square root of 6 minus 4. 3 minus 2 is 1, square root of 6 minus 4 is your solution. Remember that any time that you have three factors that you're multiplying together, first you're going to multiply two of them together, then you may have to use FOIL again. We didn't here because the product of two of our binomial factors was simply a 1. But if this answer here, the product had been, kids, I'm totally making something up. If it had been 3 times the square root of 2 minus 2, then you would just go ahead and repeat that FOIL, simplify and combine like terms, and that's all there is to multiplying these radicals. I know you can do it. You should be breathing a little bit easier in this section. That's all there is.